In this video, I'm planning on going over 4 of the problems that were in worksheet number 2 that we looked at in class yesterday. So basically, most of these problems involved specific heat, but there was one problem, or actually a couple problems that just involved some conversions. And so first we're going to look at one of the problems that involved a conversion, and then we're going to look at 3 problems that involved a specific heat in your calculation. So let's start with this one. We have a patient and it says they receive 3.2 liters of an IV glucose solution. So let's just draw our patient, and here's the IV, and this says that they received 3.2 liters. And a lot of times with these problems, I just like to draw a little picture because I think it helps with visualizing what's going on in the problem. And if you can visualize what's going on in the problem, a lot of times it's easier to solve. Okay, so we know that this patient is received 3.2 liters of this IV glucose solution. And then the problem gives us some more information. So it says there's if 100 milliliters of the solution contains 5 grams of glucose. So what does that mean? That means that for every 100 milliliters of this IV solution, there's 5 grams of glucose in that 100 milliliters. So we can write that as 100 milliliters is equal to 5 grams, and I'm just going to put glucose to specify that that's what I'm talking about. And then remember, we can write our conversion factors from this, so we have 100 milliliters over 5 grams of glucose, or 5 grams of glucose over 100 milliliters. So these two things are equivalent, and we're going to figure out which one we need to use in a minute. So what the problem is asking is how many kilocalories did the patient obtain from the glucose solution? Well, so this problem is asking how many kilocalories the patient got from the glucose solution. So in order to figure that out, we need to first figure out how much glucose the patient got, because if we can't figure out how many kilocalories the patient received if we don't know how much glucose they received. So this problem really has 2 parts. The first part, we need to determine amount of glucose that the patient received. And then for the second part, we can, if we assume that the glucose is all carbohydrates, which it's telling us to, so it's saying 5 grams of glucose and then carbohydrate, from that we can figure out how many kilocalories the patient got. So then for the second step, we're going to determine kilocalories patient received from the glucose. Okay, so let's think about this. Let's do this problem in the 2 parts. We want to start with the first part, so we're not going to worry about the second part for a minute. So the first part, determine the amount of glucose the patient received. Okay, well, let's look at this. So we know that the patient received 3.2 liters of IV solution, and we know that there's 5 grams of glucose in 100 milliliters of solution. So what we need to do, since our conversion factor is in milliliters, we want to convert the amount of solution that the patient received from liters to milliliters. So we have the 3.2 liters, and we want to convert this to milliliters. So we need our conversion factor from liters to milliliters. There's 1,000 milliliters per 1 liter. And so then the liters cancel, and we're left with 3,200 milliliters. And if you didn't remember that there were, like, sometimes this 1,000 milliliters per 1 liter, sometimes people get that backwards and they'll accidentally say 1 milliliter per 1,000 liters. So you can figure out what one's right by thinking about what makes sense. So a milliliter is a lot smaller than a liter. So that means that there has to be a lot of milliliters in 1 liter. We can't have that the other way around, because it wouldn't make sense to say that there's 1,000 liters in 1 milliliter. It only makes sense to say that there's 1,000 milliliters in 1 liter. So if you're trying to write your metric conversion and you're having trouble remembering which way it goes, think about which one's bigger and which one's smaller. And you know that there have to be a lot of the smaller ones in the bigger one. Okay, so we know how much glucose the patient received in milliliters, but that's not what we need. We need to know how many grams of glucose the patient received. So we know that there's 5 grams of glucose per 100 milliliters, so we can write another conversion. And we want the milliliters to cancel, so we're going to put the 100 milliliters on the bottom and the 5 grams of glucose on the top. So then the milliliters cancel, and this works out to 160 grams of glucose. So we know that the patient received 160 grams of glucose. So now we can go to the second part. This is where we're determining how many kilocalories the patient received from the glucose. So I'm going to write down how much glucose we have. So we have 160 grams of glucose, and we need to write our conversion. And if we assume that this is all carbohydrate, we know that there's 4 kilocalories per gram in carbohydrates. So this is for carb. So we can put that over here. So we have 4 kilocalories per 1 gram. The grams are going to cancel, and we're left with 640 kilocalorie. So this is the answer to our question. The question was, how many kilocalories did the patient obtain from the glucose solution? So they obtained 640 kilocalories. So with a problem like this, it's usually easiest to think about it in steps. So if you try to jump to the end, like how many kilocalories did the patient obtain from the glucose solution, it starts looking like it's a really hard problem. But if you just think about it in steps, like we did here, so we have step 1 and step 2, the problem becomes much more manageable. All right, let's go on to the next problem. So in this problem, we have a calorimeter, and remember that a calorimeter is for determining food calorie values. And I have a picture here so we can think about what's going on, because if you think about this problem seems really complex, but if you think about what's going on, it becomes simpler. So first of all, we have our calorimeter, and we're going to assume that this is perfectly insulated. So what that means is that there's no heat escaping from the calorimeter. So there's no heat going across the boundary in or out. On the inside, we have this container, and this container has some kind of food sample. In the case of this problem, the food sample is olive oil. And what we're going to do, we have probably an electric coil here that we're going to heat up that electric coil, and that's going to burn the food. And it turns out that we need oxygen for the food to burn. So that's why we have this oxygen going into this container. So this is basically like a mini oven, right here, and we're going to burn this food. Well, what happens when we burn this food is heat moves from the food into the water that's in this container. So all this blue stuff is water. And so as this food burns, it's going to lose heat, and that heat is going to heat up the water in the calorimeter. And then you'll notice that we have this thermometer here, so we can measure the temperature. So we're going to have a temp, so we're going to take a temperature before burning the food. So we have the temperature of the water before burning the food, and this is given to us right here. So I'm going to call that T1 is equal to 22.7 degrees Celsius. Then we're going to burn the food. Heat is going to be released into the water from the food burning, and that makes sense because if you heat something up, it's going to lose heat, and it's going to, in this case, add heat to the water. And so we have this thermometer here that's going to continue to measure the temperature, and so then we can get the temperature after burning the food. And this is given to us as I'm going to call this T2. So T2 is equal to 38.8 degrees Celsius. Okay, so that's basically what's going on in the calorimeter. We're burning food, the food loses heat to the water, and it heats up the water. And what we're going to assume to set up this problem is we're going to assume that the amount of heat that this food loses is equal to the amount of heat that the water receives. And I'm going to write that as Q food, so the energy lost from the food is equal to the Q is equal to Q of the water, so energy gained by the water. And so now let's look at what the problem says. So we have a 0.66 gram sample of olive oil, so I'm going to just say that the mass of the olive oil is equal to 0.66 gram, and it gives us the water, so it's a 370 gram sample of water. So the water is, so I'm going to put the mass of the water is equal to 370 grams. And then we want to know what is the energy value for the olive oil in kilocalories per gram. So what we're finding is the energy value, so energy value of olive oil in kilocalorie per gram. So what we want to do is think about this problem in a couple of steps, just like the last one. So the first thing we want to do is figure out how much energy this olive oil lost. Like how much energy did the olive oil lose, and we can figure that out because we know that the energy lost by the olive oil is equal to the energy gained by the water. And we're given everything we need to determine what Q of the water is. So Q is equal to MCAT. And so what we want to do is figure out the Q of the water, and I'm going to change this to olive oil and water just so that these match. So Q of the water, we know that Q of the water is equal to Q of the olive oil. And so what we want to do is figure out the Q of the water. Once we know the Q of the water, we know what the heat lost from the olive oil was. And once we know that, we can calculate the energy value. So calculate energy value of olive oil. Okay, so let's go back to number one right here. So we have the Q of the water is equal to the mass of the water, so that is 370 grams. And we need the specific heat, and it wasn't given to us, so that's something we would need to look up to do this problem. And so we can get our specific heat with either units of calories or joules. And in this case, we're going to want calories since it's asking for the answer in kilocalories. So the specific heat of water is equal to 1.00 calorie per gram degrees Celsius. So we're going to put that in right here. And the reason why we're using water is because we're calculating the heat gained by the water. So 370 grams by 1.00 cal gram degree C, and then we have the temperature change, so 38.8 degrees Celsius minus 22.7 degrees Celsius. Now let's look at our units. So the grams are going to cancel, the degrees Celsius is going to cancel, and we're left with calories, which is the unit that we want. So this works out to 5,957 calories. So basically we know that the heat gained by the water is equal to 5,957 calories, and that means that the heat lost from the olive oil is equal to 5,957 calories. And you might be wondering why we didn't apply this Q is equal to MCAT directly to this olive oil sample. I mean, it seems like why are we calculating this in the water and when we're interested in the olive oil? Well, the reason why is because since we are assuming that the heat lost from the olive oil is equal to the heat gained by the water, we can calculate the heat gained by the water, and we know that that's equal to the heat lost from the olive oil. And we're given all of the information we need from the water to calculate what Q is. So we know the mass of the water, and we know the change in temperature. And for a calorimeter, that's really nice because we can measure temperature, and we can weigh the mass of we can measure the mass of the water, and we know what the specific heat of water is. So basically, we use the water because we have things that we can measure pretty easily, and we can look up the specific heat of water. If you tried to use the olive oil, first of all, you're not given the information for the olive oil in the problem. We know the mass of the olive oil, but we don't know the temperature differences, so before and after burning, and we would have to look up the specific heat of olive oil because it would be different from water. So if you tried to do this calculation with the olive oil, you would quickly run into some problems because you don't know what the temperatures are of the olive oil before and after it was burned. But we do know the temperatures in the water, so I think that you can let the information that you're given in the problem guide you in how you need to solve it. Okay, so we have the Q of the water is equal to 5,957 calories, and this is equal to Q, or the heat lost from the olive oil. Now we want to calculate the energy value of the olive oil. So let's look at the units for that. The energy value is kilocalorie per gram. So we have calories and we have grams here. So based on these units, we know that we just need to divide the mass into the heat value. So energy value of the olive oil is equal to 5,957 calories over 0.66 gram, and this works out to approximately 9 kilocalorie per gram. And notice that I did the conversion here, so my answer was actually about 9,000 calories per gram, and then I did the conversion to kilocalorie per gram. And this is a value that we would expect for olive oil, since olive oil is mostly fat, and the energy value for fat is 9 kilocalories per gram. All right, let's do the next problem. So this one looks like it's really complicated, but it's actually kind of similar to the one we just did. So let's look at what we have. We have, it says in a building, oil is used in a steam boiler heating system. So basically what we're doing is we're, like, let's say that we have this, well, let's just say that we have this boiler. It's full of water and we're burning oil. So let's just say that this is the oil. We're burning it and we're providing heat to the water to heat up the water. And then it says the combustion of 1 pound of oil provides 2.4 times 10 to the 7 joules. So this is a conversion factor, and we don't know how we're going to use it yet, but we're going to write it down just so we have the information from the problem. So 1 pound of oil is equal to 2.4 times 10 to the 7 joules. So we're just going to leave that there for now. And then we want to know how many kilograms of oil are needed to heat 150 grams of water from 22 degrees Celsius to 100 degrees Celsius. So we have water. So we have this water here, and we know that we have the mass of the water is 150 grams, and we're heating the water from 22 degrees Celsius to 100 degrees Celsius. So that means that T1 is equal to 22 degrees Celsius and T2 is equal to 100 degrees Celsius. And so we're going to do this problem in a couple steps again. First of all, we're going to figure out so we want to know how many kilograms of oil are needed to heat that much water. 150, this is kilograms of water. So first we're going to calculate the heat required, and this is Q, to heat 150 kilograms of water from 22 degrees Celsius to 100 degrees Celsius. And then once we have that, we're going to figure out, so we're told how much heat, like in this conversion, we're told how much heat we get from, so we're told how much heat we get from 1 pound of oil. So for number 2, we're going to calculate pounds of oil to get the heat required to, or I'm going to say to get the Q required to heat the water. And then we're just going to convert that from pounds to kilograms because it wants the answer in kilograms. Okay, so let's start with step 1. And so we want to calculate Q, so we're going to use Q is equal to MCAT. And we're calculating this for the water. So we're calculating the Q, so the amount of heat required to heat 150 kilograms of water from 22 degrees Celsius to 100 degrees Celsius. So the mass of the water is 150 kilograms. And I'm going to actually just convert that to grams since I know my specific heat has units of grams. So 150 times 10 to the 3rd grams. And then I have the specific heat, and I'm using the specific heat for water because I'm calculating Q for water. And the specific heat, and I want the specific heat with joules because I'm working in joules. So the specific heat of water is equal to 4.184 joules per gram degrees C. And the reason why it's different from the specific heat we used before for water was because before we were working in calories, and the specific heat of water in calories is 1 calorie per gram degrees C. So you're going to pick your specific heat depending on what units you're working in. We're working in joules right now, so we're going to use the 4.184. So 4.184 joules per gram degrees Celsius. And then we have our delta T, which is 100 degrees Celsius minus 22 degrees Celsius. And this works out to 4.895 times 10 to the 7 joules. Okay, so now we know that this is how much heat, so this is Q. This is how much heat we had to add to the water to heat it from the 22 to 100. So now let's do step 2. And this is where we're going to use this conversion factor. So we know that 1 pound, if we burn 1 pound of oil, so if we burn 1 pound of oil, we get 2.4 times 10 to the 7 joules. So let's write down this Q first. So the Q of the water is 4.895 times 10 to the 7 joules. And then our conversion is going to be, we have 1 pound of oil per 2.4 times 10 to the 7 joules. And this works out to 2.04 pound. And then if we convert from pound to kilogram, this is 0.93 kilogram. All right, so this problem looks like it was, just reading it, it looked like it was going to be really complicated, but if we split it into the 2 steps, each step was not anything that we haven't done before. So try and think about these problems as multiple steps if that helps to set it up. All right, so now let's do this last one. So we have 100 joules. We have 100 joules of heat. Oh, so we're adding 100 joules of heat to 0.03 meters cubed of water at 35 degrees C. And we want to know what is the final temperature of the water. So really, we're looking for T2. This is T1. We're given a volume of water, so we know that we're going to need to find the mass, and this is Q. So basically, we're just going to use the heat equation. So we have Q is equal to MCAT, and let's expand out this delta T. So this is T2 minus T1. We are given everything except for T2. We're solving for T2. So what we want to do is solve this equation for T2. So let's do that. First we're going to divide over the MC. So now we have Q over MC is equal to T2 minus T1. And then we're going to add the T1 over. So then we have T2 is equal to Q over MC plus T1. Okay, so now what we're going to do is just plug in our values. So we have 100 joules for Q. Since we're dealing with water and joules, we're going to use the 4.184 joules per gram degrees C for the specific heat, and then T1 is 35 degrees. The thing that we need to look at is we need the mass, but we're given the volume. But look, we're also given the density of the water, and the units of density are kilograms per meter cubed. So that means that we can use that as a conversion factor to get the mass from the volume of the water. So the density is equal to mass over volume, and this symbol is for density. And so we want to solve this equation for the mass. So the mass is equal to the density multiplied by the volume. So this is equal to, it gives us the density as 1,000 kilograms. So 1,000 kilograms per meter cubed. and then we're given the volume as 0.03 meters cubed. And so this is equal to 30 kilograms, because the meter cubed cancels, and which is equal to 30 times 10 to the third grams. Okay, so now we have our mass, so this goes right there. So let's rewrite our equation with everything in it. So T2 is equal to 100 joules over, let's see, so 100 joules over 30 times 10 to the third grams multiplied by the specific heat, so right here, so 4.184 joules per gram degrees Celsius. And this is why I converted this mass into grams, because we had kilograms over here, and I just wrote it as grams because we have grams in our specific heat, and so we need to use grams in our mass so the grams cancel. And then we have temperature, so plus 35 degrees Celsius. So the joules are going to cancel, and we're left with degrees Celsius, which is what we would want because we're adding it to a degree Celsius and we're solving for a temperature. Works out to 35.0008 degrees Celsius, which we would round that off to 35 degrees Celsius. So basically this is a pretty large volume of water, and so we didn't add enough heat to increase the temperature by probably a measurable amount. So that's all that means. And you might have noticed originally this problem had 0.301 meters cubed. And so you would end up with about the same thing with that if you go through and calculate the mass with that volume. You would end up with about the 35 degrees Celsius. So I hope this video was helpful. Thanks for watching.